Okay, let's dive right into this critical explainer on mass and balance. Look, if you're a student pilot prepping for your DGCA CPL air navigation exam, you are in exactly the right place. We're going to completely master the physics, decode the formulas, and most importantly, dodge the very specific traps they're going to set for you on test day. But before we look at a single equation, I want you to put yourself in the left seat for a second. Just imagine it. You're rolling down the runway in a fully loaded aircraft. You hit V1, then VR, and you pull back on the yoke. But instead of that nice, smooth rotation you expect, the nose pitches up violently, uncontrollably, right into a fatal stall. You push forward, but there's literally no response. That is the terrifying real-world reality of an improperly loaded aircraft with a center of gravity that's just way too far aft. So the math we're learning today, it isn't just to pass an exam. It is the absolute foundation of your survival as a pilot. All right, here's our flight plan for this lesson. We'll start with the concept explained, move into the numbers and formulas, tackle the DGCA exam focus, and wrap up with a quick recall revision. Let's get started. Section 1. Concept explained. We really need to define the physical reality of the math that keeps us safely in the sky. The absolute core of this entire explainer is the center of gravity, or the CG. Imagine you could literally attach a giant cable to the top of your aircraft and suspend it right in midair. The exact point where that aircraft perfectly balances, perfectly level, that is your center of gravity. It's the theoretical point where the entire mass of the aircraft is concentrated. And understanding this is absolutely crucial, because an aircraft always balances, and more importantly, it rotates, about this specific point during every single flight. So let's see how this builds the mass hierarchy. This is a topic the DGCA absolutely loves testing. You start with the basic empty mass. So that's just the metal, the engines, and the unusable fuel, nothing else. Then you add the crew and their baggage, which gives you your dry operating mass. Add your takeoff fuel to that, and boom, you get your operating mass. But here's a really critical one to remember. If you take your dry operating mass and add your traffic load, meaning you're paying passengers and cargo, but absolutely zero fuel, you get your zero fuel mass. Now, you might be wondering, why do we actually care about all these different masses? Well, it's all about limitations. The maximum zero fuel mass, or MZFM, exists specifically to prevent your wings from literally snapping off due to excessive bending loads right where they meet the fuselage. We also have the maximum takeoff mass, which is a hard structural limit set by the manufacturer. But keep in mind, your performance limits are dynamic. They'll change based on things like runway length and density altitude. So the crucial takeaway here is this. You must always calculate based on both structural and performance limits, and the lowest calculated number is the one that legally binds you. No exceptions. Section 2. The numbers and formulas. Step into the cockpit with me as we break down the exact math you need to know. First up, let's look at the three variables that make up every single weight and balance sheet. First, mass. That's just the physical weight of the item. Easy enough. Next is the balance arm. Think of the aircraft kind of like a giant seesaw, and the datum is your center pivot point. The arm is the exact distance from that datum out to the item you're loading. Finally, we have the moment. A moment is essentially the rotational force exerted by that mass at that specific distance. To find it, you simply multiply the mass by the balance arm. And this perfectly illustrates the 4 simple steps to find your basic CG. Honestly, if you follow this, you cannot fail. Step 1. Multiply every single item's mass by its arm to find its individual moment. Step 2. Add up all the masses. Step 3. Add up all the moments. And finally, for step 4, take your total moment and divide it by your total mass. The resulting number is your center of gravity station. Say it with me, total moment divided by total mass. Burn that into your memory right now. Now, for larger transport aircraft, the DGCA is going to ask you to express that CG as a percentage of the mean aerodynamic chord, or MAC. I know, the formula sounds super intimidating when you first hear it, CG station minus the leading edge divided by the total MAC. But seriously, don't panic. Let's look at exactly how this works in practice. Let's just walk through a worked example step by step. Let's say your trailing edge is at 650 inches and your leading edge is at 500 inches. First, find the total MAC length. 650 minus 500 gives us a MAC of 150 inches. Simple, right? Next, let's say your calculated CG is at station 550. How far is that from the leading edge? Well, 550 minus 500 is 50 inches. Finally, you just divide that 50 by the total MAC of 150. That gives you 0.333. Multiply that by 100, and you're sitting exactly at 33.3% MAC. See? Not bad at all.
But what if you're already loaded and you realize your CG is out of limits? If you need to move cargo from one hold to another, this shift formula will save you from having to recalculate everything from scratch. The change in CG equals the mass shifted multiplied by the distance shifted divided by the total aircraft gross mass. You can also think of this as a cross multiplication. Mass shifted over total mass equals the change in CG over the distance shifted. It's a real time saver.
Okay, listen closely because this is where students throw away easy marks in the exam room. When you're adding or removing weight, never ever divide by the old mass. You absolutely must calculate and use the new total mass in your formula. Second, always visualize the aircraft. If you remove a heavy bag from the back, from aft of the CG, the nose is going to drop. That means the CG shifts forward. And please don't forget that if an arm is located forward of the datum, it's a negative number. Don't drop your minus signs.
Section 3. DGCA Exam Focus. Let's pivot straight into the exam room and tackle the actual tricky questions they love to throw at you.
All right, here's a classic question. The stalling speed of an airplane will be highest when it is loaded with a, well, read this carefully. They're basically testing your aerodynamic understanding of how weight distribution impacts your stall characteristics. So are they looking for a high gross mass, a low gross mass, a forward or aft CG? Take a quick second to think about the physics here. The correct setup is D, a high gross mass combined with a forward CG. Why? Because a high mass naturally requires more lift to stay flying. But the CG placement is the real trick here. A forward CG makes the aircraft naturally nose heavy. To keep the plane level, your horizontal stabilizer has to push down much harder. This extra tail-down force acts exactly like extra weight the wings have to carry, which artificially increases your wing's angle of attack. And a higher angle of attack means a higher stall speed. Let's look at another one. This is a classic DGCA question, testing your memorization of those mass hierarchy definitions we covered earlier. Allowed traffic load is the difference between what? Is it operating mass and basic mass? Or maybe allowed takeoff mass and operating mass? If you remembered our hierarchy steps, you already know the answer is D. It's your allowed takeoff mass minus your operating mass. Everything that you can legally lift, minus the aircraft itself, the crew, and the fuel, leaves exactly what you can sell to passengers. It's what actually makes the airline money. Also, watch out for floor-loading word problems. The DGCA might ask if a specific crate can be loaded into a cargo hold. You have to ensure the mass of the object, divided by its contact area, doesn't exceed the structural limit of the floor. If you get this wrong, it punches a hole right through the cargo floor. And trust me, the chief pilot won't be happy about that. Just remember this simple formula. Mass divided by area equals floor load intensity. And here it is, the most famous DGCA trap of all. They love to give you the maximum zero fuel mass, the maximum takeoff mass, and the maximum landing mass, and then ask for the maximum allowable takeoff mass. Do not just look at the MTOM. You have to calculate all three constraints. You take the landing mass and add the trip fuel. You take the zero fuel mass and add the takeoff fuel. Then you look at your structural MTOM. You calculate all three of those, and you strictly choose the lowest resulting number. That lowest number is your actual legal limit. Don't fall for the trap. Section 4, quick recall. Imagine we are literally 60 seconds from walking into the exam hall. Let's lock in the rules in a rapid-fire revision. Snap a mental picture of this slide right now. Ready? MZFM exists solely to prevent wing bending. Dry operating mass plus traffic load equals your zero fuel mass. A forward CG gives you a higher stall speed and more stability. An aft CG gives you a lower stall speed but far less stability. Moment is always mass times arm. And for any weight shift, just cross-multiply your mass shifted over total mass against your change in CG over distance shifted. Lock it all in? Okay, you've got the theory and you've got the formulas, but aviation is all about practice. To cement everything we've just talked about, head directly over to clouddeck.in to hammer out practice questions on these specific formulas. Repetition is exactly how you survive the DGCA exam room. Look, remember this. The math isn't just a hurdle to pass your DGCA exam. It's the invisible envelope that dictates whether your aircraft flies safely or becomes a statistic. Every single pound and every single inch matters out there. So the real question is, do you have the discipline to verify it all before taking command? Thanks for joining me in this explainer. Now go out there and crush that exam.